Nature, or should I say nature, is God's gift to this bountiful earth. I'm out here with Momin Mopis, Thomas Wessling, and myself, Nitish Kata, to discuss trees.
Have you ever been just walking and wondered, how does water get up trees? It's the great question of life, and we're here to answer it.
Hello. Somehow I've managed to find myself at the top of this tree without breaking every bone in my body. But I have muscles, and trees don't. So how do trees get water from the bottom all the way up here? Let's find out.
As you know, the earth has gravity and pulls everything down, including water. So how do trees pull the water back up?
Every tree needs sunlight, carbon dioxide, water, and minerals to survive and make their own food. Plants can acquire sunlight and carbon dioxide from above ground mechanisms, and they can acquire their water and minerals from the soil beneath them, where the roots lie. Why don't we take a closer look?
A lot of terminology involved. Trees have a tube that runs from the roots to the shoots called the xylem that transports water and minerals to where it needs to be. Another tube, called the phloem, transports the products of photosynthesis to where they need to be used.
Water has high cohesion because of the hydrogen bonds between the water molecules. Cohesion means the water molecules stick together. Hydrogen bonds are bonds between the slightly negatively charged oxygen atoms in the molecules and the slightly positively charged hydrogen atoms, brought about by the polar covalent bonds between oxygen and hydrogen. Polar covalent bonds happen when one atom wants the electron a little bit more than the other, so the electron spends more time with one atom than with the other.
The cohesion of water is one factor that lets water get pulled up, but another is transpiration. Transpiration is the evaporation of water from plants, and this transpiration helps move the water up the tree. The transpiration pull theory is also called the cohesion theory.
When ultra-pure water is stuck in an extremely small tube, the force of cohesion is enormously high, which allows water to flow up the tube. This is called the capillary action. The problem with transpiration pull theory is that the xylem sap is definitely not ultra-pure water. Up to 800 liters of water reach the top of an average tree every single day, but there is no pumping mechanism that within trees use to pump the water up. In 1895, the Irish plant physiologists H. Dixon and J. Jolly proposed that water was pulled up a plant by tension above and from above, like sucking water up a straw. A straw is a perfect example of drawing water up through pressure differences.
As you can see, Thomas exemplified the near perfect vacuum inside a straw. Fluids, such as air and water, flow from areas of high pressure to areas of low pressure. In a straw, the area of high pressure is here at the bottom, and the area of low pressure is at the top. Where Thomas is sucking creates a vacuum. Because of this, water flows from the bottom to the top.
A similar phenomenon may be said of the xylem tubes in the trees. The difference in pressure lets the water flow up the tube into the tips of the trees. You would think that the lowest pressure possible would be zero, a vacuum. Water can only go up 10 meters in a perfect vacuum, but many trees are much taller than 10 meters.
Example?
This is because trees can make negative pressures of up to negative 15 atmospheres of pressure, which actually pulls the water up the tree. This is lower than pressure in a vacuum. At this low pressure, water would actually start to boil, creating bubbles and allowing the water to become water vapor. But because the xylem has been filled with water from the start of its life, the tube is immune to bubbles and water is not lost.
So how do trees make negative pressure? Well, when you have a gas, your gas laws indicate that the minimum pressure you can have is zero, or a perfect vacuum. However, as Nitish mentioned, when you have the xylem tubes fully filled with water without any air bubbles, you're dealing with liquids. And liquids can have negative pressure. That's why we can have negative 15 atmospheres at the top of a tree and zero at the bottom. One at the bottom, and so on and so forth. This is what lets the water go from the bottom to the top.
Look, it's a deer in its natural habitat. Not really, but it's in the back of Eisenhower. It's a deer, folks. Deer and Indians. Nothing better. The Indians are trying to sneak up on the deer. It's gone.
So, why do trees even need water? For photosynthesis, or not?
Actually, only less than 1% of the water is used in photosynthetic reactions. 5% of the water is used to make new cells for growth, but the rest just evaporates. Before we can talk about psi values, we need to understand a little bit about solute concentration. Here we have an example of a hypotonic solution. The solution on the outside is your hypotonic solution, where there is less solute concentration and more water. Water will flow from the outside to the inside to balance out the tonicity. Here we have an example of an isotonic solution. You can see that there are 6 solutes on the outside and 6 solutes on the inside as well. Here, water will flow from into and out of the cell, but it'll flow in equal amounts, so there is no net transfer of water. Here, we have a hypertonic solution where the outside has a lot more solute concentration than the inside. There's less water per unit volume in the outside than there is in the inside. Because this is a hypertonic solution, water will flow from the inside of the cell to the outside of the cell to balance them out. In order to survive, plants need to balance their water uptake and their loss. Water moves through cells and living things such as plants and animals by a process called osmosis. And osmosis determines the net uptake or water loss by a cell and is affected by 2 factors: solute concentration and pressure.
Water potential is a measurement that combines solute concentration and pressure. Water potential determines the rate of water flow and the direction. Water will flow from areas of high potential to areas of low potential, similar to an object in the air. In the air, it has a very high potential in relation to the earth, while at the ground, it has a very low potential. That's how water flows, from high to low.
Water potential is measured in units of pressure called megapascals. Water potential equals 0 megapascals for pure water at sea level and room temperature.
Both pressure and solute concentration affect water potential, as stated before. The solute potential of a solution is proportional to the number of dissolved molecules, which are called the solutes. The solute potential is also called the osmotic potential. And remember, more solute means less water. Pressure potential is the physical pressure exerted on the solution. Turgor pressure is the pressure exerted by the plasma membrane against the cell wall and the cell wall against the protoplast, which is outside of the cell wall. The psi p is equal to the pressure, the psi value from the pressure that is applied on the liquid or on the fluid. The psi s is equal to the solute concentration and is always negative. As stated before, both pressure and solute concentration can affect water potential. The solute potential of a solution is proportional to the number of dissolved molecules, which are called solutes. Solute potential is also called the osmotic potential, and remember, more solute means less water. Pressure potential is the physical pressure on a solution. Turgor pressure is the pressure exerted by the plasma membrane against the cell wall. The psi p value is equal to the pressure potential, and the psi sub s value is equal to the solute concentration, and the psi sub s is almost always negative.
As you can see here, there's no pressure on either side, but you have a higher solute concentration on this side, so this is your hypertonic solution. So water is going to go from this side to that side to even out the concentrations. That's why you have a negative psi value of 0.23 here, and because it's negative, the water will flow this way. And then in example B, we have a similar situation, except this time we have a positive pressure pushing down. Thus, you have a psi p value going this way, a positive psi p value, while the solute concentration is higher here. So water will try to go here to even out the concentration, but because there's a pressure pushing this way, pushing that way, the pressures are equal and there's no net transfer of water.
Alright, now let's take a look at example C. So once again, we don't have any pressure on this side, on the left side of the U tube, so your psi p values is 0 here, and your psi s value is 0 because this is pure water. There is no solute concentration, so your total psi value is 0 megapascals. On this side, we have increased positive pressure. Now we have a psi p value of positive 0.30 and a negative psi value from the solute of negative 0.23 for a net for a net psi value of 0.07 megapascals. Because this is positive and this is 0, the water will flow from your right side to the left side. In D, we have a situation where we have negative pressure or tension pulling up on the pure water in this side. So our solute concentration, our psi value for the solute is still 0, but our psi p value, psi pressure value, is negative 0.30 for a total psi value on the left side of negative 0.30 megapascals. On this side, we don't have any pressure, so our psi p value is 0, and our psi solute concentration value is negative 0.23 again. So we get psi equals negative 0.23 megapascals. Because the psi value on the left side is lower than the psi value here, the water flows from the right side to the left side. This is actually an example of what happens in trees as well. We have negative pressure or tension pulling up on the water in the xylem tube, which causes the water to flow up through the tube.